Apollo 11. Astronauts reported sudden flashes in a dark spacecraft, and 3 missions later, NASA put a particle detector over astronauts' eyes to catch whatever was passing through them. How can an astronaut see a flash when no outside light has entered the eye? The descriptions were simple and strange. Astronauts reported points, streaks, and brief bursts while trying to sleep, often with their eyes closed or with the cabin dark. These were not lights on an instrument panel. They were visual events with no outside beam entering the eye. The word for a light seen without external light is phosphene. A rubbed eye can make one. So can pressure, eye motion, or electrical stimulation. The Apollo reports were different because they appeared in flight, in darkness, far from the protection that usually sits above a human body. Beyond most of Earth's atmosphere, the body is exposed to more ionizing radiation. Beyond the strongest protection of Earth's magnetic field, the exposure changes again. Galactic cosmic rays include fast atomic nuclei that arrive from outside the solar system. Solar energetic particles can arrive from violent events on the Sun. Both are established hazards for crews. Heavy particle exposure across the lunar Apollo missions varied with shielding and with the phase of the solar cycle. The flashes were not the danger itself. They were a signal that the danger had reached the human nervous system in a form a person could notice. NASA treated the reports as something to measure. An undated NASA technical reports server page describes ALFMED as a nuclear emulsion detector built to record tracks of cosmic ray nuclei crossing the eye area and compare those tracks with astronauts' reported visual sensations. An undated Apollo 16 flight journal page places the ALFMED experiment during day 3 of the mission, with transcript entries around 48 hours after launch and completion about 2 hours later. The apparatus was awkward, but the idea was exact. If a particle track and a flash lined up in time and place, the report became evidence. The problem was no longer whether astronauts had told an eerie story. The problem was whether charged particles passing through the head could produce a visual perception. The evidence now strongly supports that answer. Space crew reports, particle-accelerator experiments, and heavy ion cancer treatments all point in the same direction. Charged particles can produce phosphenes through effects on retinal photoreceptors, retinal neurons, and possibly other parts of the visual system. That does not make every flash identical. A particle might interact in the retina, it might affect the optic nerve, it might trigger activity farther along the visual pathway. The exact route for each event is still partly uncertain. One supported mechanism is direct electrical disturbance. A charged particle passing through tissue leaves a trail of ionization. In the eye or visual system, that disturbance can be read as a signal, even though no photon from the outside world has arrived. Another proposed route is Cherenkov light. In a transparent material, a charged particle moving faster than light can move through that material gives off a faint optical glow. In the eye, that glow could stimulate the retina. This mechanism is plausible and has been argued for since the Apollo era, but it is not the only possible pathway. A recent unreviewed simulation reports that Cherenkov light in a simplified human eye could produce retinal responses at rates consistent with astronaut flashes, with heavy nuclei, such as iron, contributing strongly. Because that result is a preprint and a model, it supports the idea without settling the biology. Shielding helps. It reduces many particles and lowers dose. But the most energetic cosmic rays are difficult to stop. Thick material can also create secondary fragments when a high-energy particle smashes into it. Blocking every heavy particle would require mass that a spacecraft cannot practically carry. That is why deep space radiation is managed rather than erased. Mission timing, storm shelters, material choices, monitoring, and forecasting all matter. The flashes are only one visible edge of that larger problem. The phenomenon did not end with Apollo. Later crews in orbit also reported light flashes, and space station work kept pairing human reports with particle measurements near the head. Low Earth orbit is still protected by Earth's magnetic field more than the Moon or deep space, but it is above most of the atmosphere. That makes the space station a partial laboratory. It cannot duplicate a Mars transit, but it can show that the human visual system remains sensitive to the charged particle environment around a spacecraft. The answer is that the flash is real, but the light does not have to be. An astronaut can see a flash in total darkness because an energetic charged particle can pass through the eye, optic nerve, or visual system and create a signal the brain treats as vision. That is established as an effect, and the particle explanation is strongly supported. What remains open is the exact biological path of every single flash and how much comes from direct ionization, Cherenkov light, or other neural effects. The smallness of the experience is what makes it unsettling. A dot behind a closed eyelid is also a human scale detector. It shows that beyond Earth's shielding, space weather and cosmic radiation are not abstract mission charts. They touch tissue, cell by cell. Any long stay on the moon and any journey to Mars has to solve that problem well enough for crews who will try to sleep in the dark. That's why Source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.